Okay, so for the last lesson, we're going to take a look at slant asymptotes. So the first part, the startup, is you're going to do a curve sketching analysis on this function. Now, I'm not going to go through it in this video. You can look at the last video for the process for how to do it, and you can also check on D2L for what the final solution is. We're going to jump right into these slant asymptotes. So, some curves have asymptotes that are oblique. That is, it is neither horizontal nor vertical. A slant asymptote is also called an oblique line, hence this topic can also be called oblique asymptotes. Slant asymptotes or oblique asymptotes. For rational functions, slant asymptotes occur when the degree of the numerator is one more than the degree of the denominator. In such a case, the equation of the slant asymptote can be found using long division or synthetic division. So remember, oblique asymptotes are the same as slant asymptotes. If I have a function where the numerator has a smaller degree than the denominator, then it's going to have a horizontal asymptote at y is equal to 0. If I have a case where the numerator has the same degree as the denominator, then I can divide out the leading coefficients to figure out that this would have a horizontal asymptote at y is equal to 1/2. But based on the information that we got here, if f of x is equal to x cubed over x squared minus 1, then this is going to have no horizontal asymptote, but it will have a slant asymptote. And we can see that that occurs because the numerator has a degree of 3 and the denominator has a degree of 2. So let's take a look at example 1. Consider the function f of x is equal to x squared plus x minus 1 over x minus 1. First question, what is the degree of the numerator? Well, the numerator has a degree of 2. What's the degree of the denominator? The denominator has a degree of 1. So like what it said, my numerator has a degree 1 higher than my denominator. So what we're going to do is we're going to algebraically determine the equation for the slant asymptote. The first thing we're going to do is we're going to do this by factoring. So if I have f of x is equal to x squared plus x minus 1 all divided by x minus 1, then I'm going to divide out that denominator. If I'm dividing out x minus 1 using what we know from synthetic division, then I'm going to have 1. I'm going to have the coefficients of my numerator, 1, 1, and negative 1. Sorry, not negative 2, negative 1. And the first one's going to carry through. I'm going to multiply that to get 1. I'm going to add those together to get 2. I'm going to multiply that to get 2. And I'm going to add those together to get a remainder of 1. Which means that I can rewrite f of x as f of x is equal to x plus 2, what I divided out, plus the remainder of 1 over what I was dividing it by, x minus 1. Well, what's happening here is if I have a graph where it's approaching a slant asymptote in the form of y is equal to mx plus b. Then I'm going to have a distance here. I'm going to have the a value where it's approaching that distance. And knowing what we know about the distance formula, the distance is equal to f of a minus whatever that point is on the slope, ma plus b. Now, as I'm getting closer and closer and closer to this y is equal to mx plus b, or my slant asymptote, the distance is getting closer and closer and closer to 0. Now, we know that the distance between the line and the slant asymptote is never actually going to hit 0, but it's going to try and get as close as possible. So the way that we put that is we say the limit as x approaches infinity for my function minus my slant asymptote is going to approach 0. If this is true, then that y is equal to mx plus b is the slant asymptote. So, given what we've already seen, if I take my function I approach infinity for it. And I take away what divided out evenly here. Then I'm going to get the limit as x approaches infinity for x plus 2 plus 1 over x minus 1 minus x plus 2 which is going to leave me with the limit as x approaches infinity for 1 over x minus 1 and we know that that limit is going to approach 0, which means y is equal to x plus 2 is the equation of the slant asymptote.